Okay, I think we'll probably make a start. Good morning, everybody. Welcome to this webinar today, which is being delivered by the EIDF Tees Valley Hydrogen Innovation Project, which is run by Teesside University, and in collaboration with the Materials Processing Institute. I'm Simon Bradshaw, and I'm the project manager looking after the Tees Valley Hydrogen Innovation Project. Just before we start, just to go through a few housekeeping items, please. The webinar, as I said, is being delivered as part of an ERDF grant-funded project, with, as I said, with the Materials Institute today. I'll be grateful if you could please write your name, company, and if you have any sound issues in the chat. The session is being recorded. Presentations and video will be made available to all of you after the session. Please write any questions you have in the chat box. Questions will be answered at the end of all the presentations. Please can also ask you to keep your microphones muted, and please switch off your camera. Just in case people are not aware, have used Teams before, this shows you the setup of how to run things in Teams, how to turn your camera off, your microphone off, also where to actually you can put a question into the chat session for today. Okay, so the agenda today. So I say I'm giving a welcome presentation and a brief overview about the Tees Valley Hydrogen Innovation Project, which is being run at Teesside University. We will then follow on with a presentation from Venkat Krishnan at Teesside University around the hydrogen economy and towards decarbonisation. We then have two presentations from the Materials Processing Institute around steel making and hydrogen, one by Oliver Milling and another one by Richard Burley. And then after that, we'll have a question and answer session when everybody can, the questions you put in the chat section, will have the opportunity to then have the questions answered by the team. Right, so apologies. So quick housekeeping, apologies. Didn't realise my microphone was muted. So just a brief overview of housekeeping. So this session is being recorded. If you have any questions, can you put in the chat box? Questions will be answered at the end of all the presentations. Can you keep your microphones muted and your camera off, please? In case you're not aware for housekeeping, how to use Teams, this shows you where you can turn your camera off, your microphone can be muted and unmuted, and also the chat function where you can ask questions of anybody today. Okay, so the agenda again is myself to give an introduction about the Hydrogen Innovation Project, and then we'll have some presentations from Venkat Krishnan to talk about towards decarbonisation and an overview. And then we'll have two presentations from the Materials Processing Institute covering steel making and hydrogen and challenges of production of hydrogen for the steel industry. Okay, just a brief overview then about the Tees Valley Hydrogen Innovation Project. So this is a commercial project which is run by Teesside University, and it's ERDF fully funded project to support SMEs in the Tees Valley region to develop new products, processes or services for the hydrogen economy. We have a target of assisting 44 SMEs in the region, of which we are currently assisting 29. And we also have to help a number of companies to develop a number of new innovative technologies. And we have a hydrogen laboratory space, which we'll talk about later on in the presentations today. Each company gets a minimum of 12 hours assistance, and the duration of the project at the moment is till the end of June 2023. Some areas of focus from the project include blue hydrogen production, purification, hydrogen safety, catalysis, carbon capture, storage and utilisation, and also photocatalytic reactions. So there are a number of companies I just want to briefly just talk about that we are supporting through the Tees Valley Innovation Project. A company called Irico, which is looking at innovative graphene-based materials for hydrogen storage. X-Heat is a company looking at, it's developed a gas catalytic heating system, and we're helping to look at them for hydrogen use. Derby Tech, which is a company which is developing a training reactor. Micropore Technologies, who are helping us on the catalytic membrane, and also Teesside University ourselves, our own hydrogen reactor space that we've got. So the university has a catalytic membrane reactor based on steam methane reforming process. We have laboratory space on the 8th floor of the tower to the university. We are just at the stage of actually commissioning the reactor. One of the key focuses of using catalytic membrane technology that we're developing is that you can reduce the CO2 emissions and reduce capital costs by combining several stages of the SMR process into one. So this reduces costs, it reduces the hydrogen production costs, and also CO2 emissions over the standard SMR technology. So as I mentioned, Irico is a company that is developing hydrogen storage materials based on graphene. A very innovative company, and we are helping them to sort of do some blue sky development work to hopefully to the point of proof of concept to show how graphene type materials can be used to store small quantities of hydrogen from the natural environment. X-Heat, as I mentioned, is another very innovative company that we're supporting at the moment. They have a process of using a gas catalytic system which actually creates infrared heat. They are at TRL level 5 on the development level, but we are supporting them to look at how to convert that technology to run on hydrogen gas. And they'll be one of the people that will be actually using our hydrogen demonstrator laboratory space at the university. Micropore Technologies is another company which Venkat will talk about in his presentation later. They do a range of membrane-based materials for emulsification, encapsulation, crystallization solutions. So it's a natural fit for them to actually then look at how their skills and knowledge and capability could then help with us as a project to then look at generating a catalytic membrane for the hydrogen reactor. And they were actively involved in working on this project, and we will in the future be putting their membrane technology then into our reactor and actually testing the durability of the process. Just some other research areas to talk about at Teesside University. So we have a lot of expertise in carbon-based energy systems, carbon capture, storage, carbon utilization, advanced combustion. On hydrogen, we've got people with experience in safety, production, purification, geological storage locations, biohydrogen, electrochemistry, from fuel cells to green ammonia, energy integration and control, and other life cycle analysis and so forth. We have a lot of expertise at the university, and we'll very much be interested to work with anybody who's interested in any of these areas of research. Either talk to myself, which is Simon Bradshaw, or to any of the team that are here today. Just a final few points. The university is also collaborating with a number of industrial partners in the region. So these include a conversion of excess of industrial energy into hydrogen, decarbonisation of marine ships, energy systems integration and microgrids, and testing of hydrogen heavy-duty vehicles in logistic operations. We have a lot of experience in geological hydrogen storage, and we also well placed with the North Sea around here for having offshore storage potential for hydrogen, and hydrogen production from waste. I'd just like to say thank you very much for your time today and joining us. I would now just like to introduce to you Dr. Venkat Krishnan, who is a chemical engineer with many years of experience working in industrial R&D. product development in areas of chemical engineering, catalysis, and reaction engineering. In solid-state electrochemistry, primarily solid oxide fuel cells. In process design and in ceramic processing. He has worked on numerous Innovate and Hydrogen 2020 programs. Venkat, over to you.
Okay, thank you. I will now share my screen. Just 1 minute. Okay. Everybody can see it?
Yep, I can see. Yep.
Oh, okay, good.
Just need to bring that full screen.
Yeah, I'll just.
Perfect.
And can you see the full?
Yes.
Okay, very good. My talk is a bit of a lead off, getting everybody back to the basics on the hydrogen economy and where we are headed. And after my presentation, Materials Processing Institute will be going into the details of steel making and the application of hydrogen in the area of steel making. So to begin with, let me just reiterate many of the things that I'm going to be talking about is well known to a few people. And if there are some people who are not that well versed in this, this might be a good opportunity to grasp some of the basics. And that's the reason why I'm calling this like an overview towards hydrogen economy and decarbonization. To begin with, the hydrogen production options that you hear a lot about everywhere nowadays, particularly the coloring of hydrogen. You know, you keep hearing about different colors associated with types of hydrogen that's being produced. You've got brown hydrogen, which was the old way of making hydrogen by the production of syngas, which incidentally was produced by using coal and by other solid fossil fuels. And when the emissions are directly released to the air, this whole process is known as brown hydrogen. The hydrogen that's produced from here is known as brown hydrogen. The hydrogen, then we came into the natural gas age, where the primary fossil fuel for producing hydrogen became natural gas. And many of us are aware that hydrogen, one of the biggest markets for hydrogen is in the fertilizer industry, in the production of ammonia, and from ammonia it goes to urea. Notwithstanding the large-scale consumption of hydrogen in the hydrocracking and hydroprocessing units, as well as in hydrogenation plants for vegetable oils. So these are the standard drivers for hydrogen production. And natural gas became, therefore, the most abundant source for hydrogen by using steam methane reforming. And that is now classified as gray hydrogen. Now we go along a little further. Now there's a tremendous amount of, since there's a incredibly high capacity for producing hydrogen, gray hydrogen, this gray hydrogen can be transitioned into blue hydrogen, where instead of all the associated emissions being released directly to the air, the carbon dioxide that's produced is now captured. And once that happens, we call it blue hydrogen. And this is obviously an area of immense interest, at least as a transition, before eventually the green hydrogen kicks in. And the green hydrogen is what is the ultimate form of producing hydrogen by renewable sources and renewable electricity. If you are looking at splitting of water via electrolysis, if that is done entirely by renewable electricity, then that would classify as a green hydrogen. Similarly, hydrogen that can be produced from biogas, and biogas coming directly from agricultural waste, agricultural products, would then be classified as green hydrogen as well. So having said that, just a couple of slides on recapping what gray hydrogen is and the state of the art in that area. Typically, natural gas undergoes desulfurization. Then if it contains higher quantities of hydrocarbons, which can be represented as CN, then it would go through a pre-reformer. And in the pre-reformer, you will get a syngas conversion and a little bit of methanation, which will give you methane. And then the main reformer comes in, where you have the classic steam methane reforming reaction, followed by a little bit of water gas shift equilibrium. And eventually this is taken all the way to a water gas shift reactor to get rid of all the carbon monoxide to carbon dioxide and maximize the hydrogen production. You will observe here that the reformer is highly endothermic process, and hence it requires a considerable amount of fuel which is burnt to provide that much amount of heat to maintain the temperature here, which basically means enormous amount of flue gas comprising of carbon dioxide is released. So while carbon dioxide is released not only from the methane feedstock, which eventually gets converted to CO2, but it's also released from the burner from the fuel gas. So that is one of the biggest problems. Now, obviously, then there is a water gas shift reaction as well, which makes the hydrogen with the desired purity grade that you want. And even the shift reactors are not enough to produce hydrogen to the required grade purity, depending on what its use is. Particularly in the new markets which are coming up for fuel cell electric vehicles, which operate with PEM fuel cells, the purity requirements are almost 5 decimal places worth of purity, is 99.9999. And for that, you would require nothing less than a pressure swing adsorption unit. And even that might not be satisfactory in certain cases. So therefore, there is a significant challenge here. So in light of all these challenges, you've got yourself a process which has got almost 3, 4, 5 steps, starting all the way from desulfurization to pre-reforming to reforming, water gas shift, pressure swing adsorption. So, and in the process, considerable amount of carbon dioxide is released as well. Now, when blue hydrogen comes into play, the carbon dioxide is absorbed. This is the traditional process, industrial operation for absorption of carbon dioxide. And you use basic solutions like amines to get rid of the CO2. But then the CO2 is then concentrated and then can be used for a variety of applications. And obviously then the solvent has to be recycled back. It is quite an energy intensive process. And these are the new ones which are coming up, which will balance the heat load here for this and make the process more efficient, which is using membranes and coming up with better and better. So these are seen in conjunction with the existing absorption processes. So this is probably representing the future as far as blue hydrogen is concerned. However, from a Teesside University perspective and from the ERDF funded what is called Tees Valley Hydrogen Innovation Project, TVHIP, what we have decided is that we would like to explore further the whole idea of process intensification. Process intensification is a vital approach, which is increasingly getting popular in the chemical industry, where you combine many processes into one big unit. And the whole idea in this case is, this is just your standard stuff, syngas generator, water gas shift reactor, pressure swing adsorption, and all these three things can be combined in one shot membrane reformer. So not only are you undergoing steam methane reforming, you're also doing the water gas shift reaction, and you're producing hydrogen, ultra high pure hydrogen in one shot itself. What are the advantages? The advantages, as you will see, is lowering the heat requirements. Because of the removal of hydrogen, you are improving the equilibrium characteristics. And eventually, because you have lower heat requirements of the furnace, you will lower the carbon dioxide emissions here. And in this regard, we are working together not only with the technology part of it, but we're also working with SMEs. And Microboard is a very interesting example here. We've been working with them. And because they have a tradition, they are already very much interested in, of course, their product is slightly different. They're involved with micro emulsions, and those emulsions are made, they're very, very carefully directed by using well-controlled pore sizes, which they have obtained in their metallic systems, porous metallic systems. So we believe that we can use something similar to them in making a composite catalyst membrane material, which I'll talk about a little bit in a couple of minutes. So there seems to be some sort of a synergy in using their materials and making our product with it. And Microbo is very much interested in seeing how these kind of products can then be developed further. Regarding membrane separations, this is an old science, but the devil is in the details. How well we develop the engineering product, that's where it counts. The idea is simple. As soon as the hydrogen is being produced, as soon as the syngas is being produced, the hydrogen is selectively removed. And once the hydrogen is selectively removed, you shift the equilibrium in the forward direction, and therefore you induce much more highly efficient conversions. And we did a lot of initial process calculations, which showed us very nicely. If you see the red and the black here, it tells you that the CO2 emissions can be lowered to almost 40%, by about 40%, if one were to lower the temperature of the reactor from 850 to 600 to 650. And for people who are familiar with steam methane reforming, you are well aware that most industrial reformers will be operating at least about 850. So that's what you require. But because of the presence of the membrane and the removal of hydrogen, you can potentially bring it down by almost 40%. So having said that, some of the work that we are doing in our laboratory right now, as of now, is trying to establish this triple layer system where you've got a palladium membrane followed by a catalyst which is coated into a porous metal substrate. And the entire technology development lies in how well we can make this multiple layered system, so that you have very good adhesion of the catalyst coating with the metallic substrates and the dense membrane, how well it can adhere to this. And at the same time, you essentially you have a process intensified system here. And over time, obviously, we're trying to lower the thickness of the palladium membrane as well, so that lower the thickness, the higher the permeability, and higher the process efficiency. So this is an area. This is the technology part of the Tees Valley Hydrogen Innovation Project, and there are a lot of opportunities here. We can integrate some commercial membranes. There are a lot of commercial membrane manufacturers also available, but the trick is how do we integrate them together with this composite reactor separator geometry. And in this process, there's a lot of focus on from our side on advanced catalysts, which inherently give you a much higher reformation activity, and at the same time the details associated with making robust catalyst coatings with high stability. Closely allied to this is the usage of different kinds of membranes for carbon capture, and this is another part of our team is very much involved in carbon capture. And this is that earlier I had shown you this, but the whole idea here is to generate hybrid processes for carbon capture, which basically means how do we generate good membranes with good significant carbon dioxide permeability. And this is an activity which is pursued by some of my colleagues, and this relates to membrane permeability experiments and also new materials for carbon capture. So this is also part of the TVHIP project. So now we come a little bit to the state of the art of as far as green hydrogen is concerned. Most of us are aware of the fact that in order to generate green hydrogen, you have to have renewable sources of electrical power, which basically either comes from wind or solar. It could also come from biomass. It could also come from geothermal methods. But we all are very much aware of the fact that this kind of power is always intermittent. So obviously there has to be some kind of energy storage systems. But at the end of the day, either we have some kind of alkaline water electrolyzers. We could also have polymer electrolyte membrane electrolyzers. These are the two major technologies that are existing nowadays for low temperature water electrolysis. And these are ideal for quick startups and particularly for reversible applications. And the fact that reversible applications are critical because it's for grid balancing. Grid balancing is the big buzzword in this area. And you already have major companies who are big players in that area as they seek to balance the power. And then having said that, it's also important for us to remember a little bit about the thermodynamics associated with PEM, low temperature electrolysis. Low temperature electrolysis requires about 286 kilojoules of energy per mole of water, which can get converted to hydrogen. So therefore, this is met primarily with the Gibbs free energy and with the T delta S, which is the heat. So if you were to take the total amount of energy required and convert it into voltage, you will require at least 1.48 volts and higher to operate this. And given the inherent efficiency of most PEM electrolyzers, you will find that PEM electrolyzers operate anywhere between about 1.6 to 2 volts per cell. This is the data that's mostly available for. Of course, the target is to get higher and higher efficiencies, but the efficiencies are pretty much not going more than 75%, at least. In some of the Siemens electrolyzers, they have reported about 75% efficiency. But the interesting thing is, when you go away from the water electrolysis and go into the domain of steam electrolysis, you will find, and this is not rocket science or anything, because it's kind of intuitive, that now you got steam, and the energy required to split steam is lower than the energy required to split water, primarily because of the latent heat of fusion, latent heat of vaporization associated with water to steam. And here you will find that the electrical energy required comes down very significantly, and the thermal energy demand goes up. So the higher you go in terms of steam, you have more favorable. It's a very favorable system as far as electrical demand is concerned. So, and you will observe that in this case, if you want the total amount of energy required to split steam under these conditions, you only require 1.285 volts to split. Compare that to 1.48 that's required to split water. So this is normally known as what you would call it thermoneutral voltage. That's the voltage required, minimum amount of voltage required to actually split either water or steam. And you can observe here that the energy required in terms of kilowatt hour per kg of hydrogen produced is about 40 kilowatt hour for water. And as we go on in the domain of steam, we end up bringing this by a pretty significant amount actually. Of course, in reality, it's a lot more. This difference is a lot more because the power consumption for PEM electrolysis is significantly higher than just what has been mentioned here. And because the efficiency of the PEM electrolyzer is actually lower. And if you are, so what does that basically tell you in terms of a process point of view? If you have high grade heat available, either from a nuclear power plant, waste heat from burners from different processes, or rather interestingly, even from steel plants, you are basically looking at an opportunity to generate superheated steam. And once you have generated superheated steam, you're talking about a very, very high efficiency hydrogen production process. And if you are able to generate a reasonable amount of superheat, which is compatible with the operation of the solid oxide electrolyzer itself, then you can operate the system under thermoneutral conditions. And when you do that, you've got an electrical efficiency of 100%. If your steam superheat is lower than the temperature of operation of the SOEC, then you have a situation where you'll have to flow more, you'll have to impose more voltage on the SOEC stack, which results in more current, and more current means more ohmic heat. And that ohmic heat will then give you the required amount of temperature, and therefore it will lower your efficiency. But still, in most of these cases, the efficiency is much, much higher than it is for PEM electrolyzers. So this is a very interesting option. I brought this up primarily because this talk is going to be, today's session is going to be addressing the steel industry. And whenever we have such high temperatures involved, the potential of generating superheated steam is very good. And if you have superheated steam, you've got the opportunity to generate hydrogen at high efficiency. Okay, just a few concluding slides. The there's a fair amount of research and technology challenges, and we are at Teesside University are very much interested in some of these areas. In the thermal tech, there is, I don't know whether this has been mentioned, but if you're aware that there's a net zero carbon center which is being set up in the Tees Valley. We have a new laboratories which are hopefully set up in the next 1 year or so on hydrogen and decarbonization and thermal technologies. So some of our projects can achieve fruition there. We're going to have some big setups in that area. And there are some research areas within electrolyzers regarding cathodes and anodes for both high and low temperature fuel cells, which will give you high performance, low degradation, and also use non-platinum group metal formulations. In addition to it, there are some interesting niche areas as far as manufacturing methods are concerned for electrolyzer cell components. And this is as far as electrolyzers are concerned. And then after that, our traditional research on steam methane reforming and biogas reforming, where we are still looking at some issues associated with catalyst stabilities to impurities and so on. And as far as carbon dioxide capture is concerned, membrane assemblies, and also resistance to degradation by poisons when it comes to membranes for hydrogen production. And for carbon dioxide capture, there's a lot of activity going on improving the permeability and perm selectivity as far as these are concerned. Then as far as steel production is concerned, one of the areas that we believe as the university that we can play a good role in the future, and we've been having some discussions on this with our prospective collaborators at Materials Processing Institute. There's a good opportunity for us to work a little bit more on direct reduction of iron in the future, where the famous the emerging DRI approach to reducing iron ore directly with hydrogen. So there were some interesting opportunities there to work together, and also the potential of using high efficiency solid oxide electrolyzer cell, but thermally integrating it with steel plants. So this is an area where we are thinking about. There's a good amount of synergy with the institute. The opportunities for hydrogen usage within steel plants, carbon capture in steel plants, that is the other part of our work. Then reactor furnace designs, there are some focus areas in that, which some of my colleagues are very much interested in, particularly computational fluid dynamics and reactor and process modeling. This is one of those areas that I talked about just a few minutes back. Hydrogen as a reducing media for iron production, and then solid oxide electrolyzers integrated with the steel industry. In summary, this was just an overview on blue hydrogen using natural gas with carbon capture. That seems to be the broad focus area for TVHIP, which is ongoing in our university. And as closely related to that is our focus area, which is the catalytic membrane reactor steam methane reformers, which is in progress right now. Then the near future, we are looking at more and more getting into the electrolyzer areas, both PEM and SOECs, where we're looking at some of the materials and process design, electrochemistry. And then finally, we have excellent opportunities to collaborate with the Materials Processing Institute in the future, and exploration of areas not limited, though, to the DRI as far as steel making is concerned. And there are many of us in this team, and the primary people in this area I've highlighted right now. That's me, and then my colleague Manu and David. They are very much involved in the circular economy and materials processing. Faizan, my colleague, is the carbon capture person, membrane hybrid technologies. And of course, Simon and Ruben are there for all other needs associated with the hydrogen economy. I'll stop there and take any questions. Or maybe at the end of the day.
Yeah, Venkat, we'll take questions at the end.
At the end. Yeah, sure. Okay. Okay, thank you.
Okay, Mark. Mark, are you here to give an overview from the Materials
Hello?
Processing Institute?
Hello? Can you hear me?
Yes, can hear you. Yeah.
Apologies, I think I unmuted and someone presses the mute button at the same time. Good morning, everybody. This is Mark Allen from the Materials Processing Institute. It's very good to welcome you to this joint event that we're participating in with Teesside University. I'm just here to introduce some of our research team to talk through basic issues, but Oliver, if you could, next slide on this one, please. Next slide, popping up. The Materials Processing Institute has been active in the Tees Valley since, in various guises, since the end of the Second World War, really. But in recent history has become an independent entity, building on literally generations of knowledge and experience in addressing technical challenges decade by decade within the iron and steel industry. And now we actually focus on, with that core, we're also focusing on the pillars of advanced materials research and development, which has always been there, and the new challenges of digital technology, Industry 4.0, the circular economy, and industrial decarbonisation. So really, Oliver, kind of next slide, please. If we look at those general areas, what we wanted to do today was really say, before we start talking about hydrogen and steel together, what are some of the basics that you should know about hydrogen? What are some of the basics about steel? And then to continue these series of webinars looking at the more specifics. I won't go into much more detail about the institute itself at this point, because it's there online. Particularly, I'd recommend have a look at some of the industry papers. If you Google us plus industry papers, there's a goldmine of resources there on where the latest thinking and calls for action are, as well as access to other training and education resources. Next slide, please. This is a critical question for us all. You want to be making green steel. We want you to be making green steel, and it's an area where, you know, we're under pressure. Really, there is even yesterday, you know, articles about is the UK steel industry is stuck on the starting line? How are we going to get from where we are now to where we want to be? So this series of webinars is a useful catalyst for some talking points, and we'll continue with more seminars in the autumn in the next academic year. But in the meantime, what we do want to be doing is getting in touch with you and you getting in touch with us to start working now on practical next steps, actually getting the ball rolling this year. Could I have the next slide, please, Oliver? Because we have a fantastic opportunity within the Innovate UK PRISM funding programme to start developing in the UK, the pilot size bits of kit that we need to join the dots from the lab-based and desk-based research and thinking that's going on to the actual real-life industrial applications and step changes that are going to be needed alongside the gradual decarbonisation that we're doing already in energy efficiency, circularising the economy and this kind of thing. So this is really to be aware we're using this opportunity to present some of our thinking about where hydrogen can fit in to iron and steel production, but this is really just an opportunity to gather you together as well and say, let's start talking in detail. We'll look at some of the challenges at the end of Oliver's presentation, but we want to be producing and creating, starting this year, the right levels of pilot size equipment that is going to meet the needs of industry in this country now, and also fit in with what's going on globally, help us to get from that starting line position and start really taking a lead where we can in the application of hydrogen as one of the solutions to get us towards a net zero future. So having said, I will now hand over to Oliver, one of the members of the Institute's Decarbonisation group, to start talking about steelmaking.
Thank you, Mark. This presentation has been put together in collaboration with my colleagues Tony Parkinson and Colin Atkinson, and also Richard Burley, who will talk about the challenges of producing hydrogen for the steel industry later on this morning. So I'm going to present an overview of steel making, how we make steel, how much the challenges of decarbonising it, and what the processes are, and the opportunities for using hydrogen in those processes. So there's two primary methods of steel making. One is using the basic oxygen furnace, and the other is the electric arc furnace. Now, between these two methods of making steel, the world makes a lot of steel. So world steel production in 2019 was approximately 1.8 billion tons. And this slide shows the production from the three main methods of steel making: basic oxygen steel making, arc steel making, and an older technology called open hearth steel making. And from this slide, we can see that over the last 50 years, the oxygen steel making has become the main route for producing steel around the world. It now produces over 70% of the world's steel. The electric arc furnace production has grown to now be over a quarter of the world's steel making, and the open hearth furnace, which is an older technology, is gradually falling by the wayside. So how do we make steel using the integrated basic oxygen furnace, or the BOSS route? Well, we start with the blast furnace to make iron, and the main inputs for the blast furnace is we use coal to make coke, which is a purified form of coal, and then iron ores that can either be lump ores and pellets, or fine ores that are sintered into larger pieces. These are then fed into the blast furnace together with limestone fluxes, and hot air is blown into the reactor, resulting in molten iron being produced. From there, the iron is taken into the BOSS converter with scrap steel. Oxygen's blown into the steel, and iron is converted to steel. From there, we move on to secondary steel making, where steel is alloyed. It's then cast and then rolled into finished products. This method of producing steel is the most common in the world. It has very high capital costs, and in order to return payback on investment, high output level must be maintained. There's also a need for continuous operation. One of the main issues with blast furnaces is that turning them off is extremely difficult. It can take weeks to turn them off, and even larger amounts of time to turn them back on again. So once a blast furnace is in operation, it's generally used until it next needs relining, which is a period of over 10 years in most applications. It also produces quite a lot of CO2. It's about 1.8 to 2 tons of CO2 per ton of steel produced. It is, however, a very efficient process, and it's become increasingly efficient over the years, and that's the main reason that it's used so widely. So in the basic oxygen converter, which is also known as the basic oxygen furnace, or the LD or Linzdorf converter.
Oliver, sorry to interrupt, we've lost your presentation. Do you want to try and share your content again, please?
Oh, sorry.
I
Yeah.
think somebody's taken over and trying to show their screen.
Hang on. I just. Can you see that again, Simon?
Yes, thank you. Sorry for interrupting.
Yes. No, that's okay. It's good to know when the picture drops out. So here we can see the basic oxygen converter. There's a photo of vessels on the left and a diagram on the right. And scrap steel is charged into the converter, partly as a coolant and partly because it's advantageous to recycle as much steel as possible through the process. And so between 5 and 20% of the steel is recycled. Then iron from the blast furnace is poured into the converter. An oxygen lance is then lowered down towards the liquid and oxygen is blown in. And this is an exothermic process. And what happens chemically to turn iron into steel is that the carbon and silicon that are present in iron are driven out and reduce the carbon and silicon down to very low levels. Impurities such as sulfur and phosphorus are also captured in the liquid slags that form on top of the melt, and that purifies the steel. Because it's an exothermic process, even with the scrap cooling, the temperature rises from about 1300 to about 1700 degrees during the process. But the iron is refined from about 95% iron to over 99% iron, and that is a conversion from iron to steel. This is a picture inside the vessel showing you what you end up with before you tap the steel out into ladles for further refining, and you have a viscous, a yellow hot liquid that actually flows in a very similar manner to water. And that simply is there's a very quick overview of basic oxygen steel making. The other main process route is electric arc steel making, which is generally smaller scale to the integrated Boss route. And the liquid steel is made from a mixture of materials, mainly steel scrap, also direct reduced or hot briquetted iron, and sometimes iron from a blast furnace is put into the electric arc furnace. And an arc is struck up. An electric arc is struck using electricity, and the heat from the arc melts the steel. Once the steel's melted, it goes to secondary steel making for alloying, similar to before being cast and turned into finished products. It's used very commonly for engineering and stainless steels. It can also be used to make a lot of long product steels, that's steels for beams, bars, rod, and many strip steels, which are what are used for automotive and many household objects. It's an efficient process, it's low cost and flexible. One of the big advantages it can be turned on and off according to demand. So if demand is low, you can turn the furnace off completely without affecting future operation. And if demand is high, you can still run it continuously if you require. It's also about 20% cheaper to produce equivalent qualities than the Boss route, and has lower CO2 emissions. On this next slide, I was explaining energy use in the arc furnace. So the primary energy source for the electric arc furnace is electricity, but it's not the only energy source. There's also supplemental chemical energies used to increase the melting speed and consistency. And typically 30 to 50% of the energy used is chemical energy. So in the diagram of the furnace we see here, the electrodes melt in the middle, and that can result in some cold spots towards the edge. So we use burners from the edges of the furnace to increase the melting rate and prevent cold spots. And different plants will use different systems, but typically gas, oxycoal, and oxygen jets are used to melt and refine the steel. So carbon is often also added into the scrap mix as a fuel, which is then burnt by injecting oxygen whilst the steel's melting, and that adds energy to the process and promotes the melt. And this is an example of some of the this type of scraps we use in arc steel making. One of the biggest types of scrap we use is industrial scrap. So this is usually offcuts from factories producing wire or car bodies, any steel product. Offcuts usually come quickly back to sites to be melted back down and recycled. There's also civil engineering scrap, which is beams from construction or demolition, and also rails. There's a significant amount of rework or scrap on any steel works, so it can be several percent of the production actually ends up being cut off, or if there's quality problems, alloying problems, things break or go too cold, those then get recycled from around the steelworks or from one steelworks to another. There's wastes or general scrap, and that can be anything from baled cans and cars to the metal from the waste skips that we'll commonly see in a scrapyard. It's also hot briquetted iron. This is usually produced as part of a direct reduction process, where iron ore is reduced to produce a fine iron powder that's then briquetted into these type of briquettes that are easy to handle, and those can be loaded straight into an arc furnace. The advantage of using hot briquetted iron is you don't end up with you end up with fewer residual alloys from scrap materials. Whichever way you make your steel, this is what you end up with. You end up with a ladle of yellow hot liquid ready for alloying and then casting and rolling into product. So if you look at the advantages of the different processes, electric arc furnaces generally cost a lot less to set up than blast furnace and basic oxygen furnace plants. Usually several billions of less to make in the first place. They have a lot of flexibility with materials. You can use up to 100% scrap in the process. You're not reliant on molten iron. If you wanted to make steel directly from ores, you can use direct reduced iron or hot briquetted iron, and they can be turned on and off as required. They also have a wide product range, particularly with engineering stainless steels, long product steels, and many, but not all strip grades, because there's a restriction due to the nitrogen that gets introduced into the alloy. It's also environmentally desirable because there's a large amount of recycling and lower CO2 emissions. And there's ongoing process improvements are always reducing the energy and emissions from the process. The challenges for arc furnaces is that a lot of the electricity that's used produces CO2. So it's never going to be a CO2-free, or at the present, it's not a CO2-free process, as well as the extra chemical energy we put in, which generates CO2. Electricity prices are also significantly higher per kilowatt hour than it is for using chemical energy. Hence the incentive to use as much chemical energy as possible as you can in the process, because it's just cheaper. Scrap prices are also relatively high compared to the iron ore. You also get metallurgical issues due to residual alloys and higher nitrogen levels in the steel produced, and that limits some of the alloys that you can make. There's also finite scrap in the world, so we rely on steel being used and then properly recycled in order to get the scrap to go into arc furnaces. And particularly when countries are developing, steel is used much faster than it comes through the system. So there's a much shorter supply of scrap in countries that are developing faster than in more mature markets like Europe. Also, high quality direct reduced iron, which we can use for producing steel using an arc furnace, in order to make steel directly from ores, is in quite short supply. So many blast furnace boss plants have a long lifetime left, often more than 40 years. So it doesn't make economic sense for the operators to close these plants. And new technology for carbon capture may enable them to be used until the end of their life. Direct reduced iron production also currently uses a lot of natural gas and coal. All this adds to a big challenge to produce iron and steel without producing CO2. So on this next slide, we can see the amount of CO2 that's produced whilst producing a ton of steel. So for a blast furnace, basic oxygen furnace route, we typically produce 1.8 to 2 tons of CO2 per ton of steel. The arc furnace is a lot better, typically producing only 0.4 tons of CO2 per ton of steel. But we know that we're still going to need to be producing about half the forward projections show about at least half the steel produced in the world is going to need to be made directly from ores. So the alternative way of doing this, using direct reduction and then an arc furnace, we can see that if coal is used to directly reduce the iron and then use an arc furnace to make the steel, it actually produces more CO2 per ton than using a blast furnace. If we use natural gas, we still produce 1.4 tons of CO2 per ton of steel, which is obviously still a lot of CO2 and needs to be reduced massively. And this is where hydrogen can come into the picture. So if you look at the diagram of a typical integrated blast furnace boss steel making route, starting with the ironworks, moving through to the steel plant, casting and rolling, we see where hydrogen can be used as a process. So a place where it could be used is it can be used in sintering iron ores. There's currently work looking at using hydrogen as a fuel and an auxiliary reductant in the blast furnace to reduce the CO2 emissions. There's a lot of natural gas used just for preheating vessels so that the refractories are conditioned before hot liquids are poured into them. And also preheating parts of the continuous caster, the molds and the ton dishes used in that process. There's also generally when steel's cast, it's allowed to go cold and then reheated for rolling or forging. And there's that large potential to use hydrogen in reheat furnaces instead of natural gas or coke oven gas that's currently used. Now, direct reduced iron is made by heating iron ore, typically iron ore fines, to a high temperature and reducing atmosphere. Most DRI is produced using coal or natural gas to produce carbon monoxide and hydrogen reductants. They reduce your iron ore to iron. There is the potential to produce DRI using only hydrogen, and that's an area that we're currently looking at, and there are several projects around the world looking into the possibility of doing this. So in summary, I've shown that steel can be made using an integrated basic oxygen route or the electric arc furnace, but it uses large amounts of energy, produces large amounts of CO2. And there's a challenge to try and decarbonize whilst maintaining very high levels of world demand. But there are numerous opportunities to use hydrogen in the process to use this. And this is just a short list of some of the areas that are currently being researched for use of hydrogen in the process. And but it raises quite a number of issues that need significant research and work in order for it to become a viable fuel to use in a mass industrial process. Over to you, Mark. Back to you, Mark.
Thank you, Oliver. This has just been popping up in between our two presenters to say there is the list of issues required research. It's not an exhaustive list. We could spend an entire day just laying out the research and development issues and challenges. that face us, and that we actually need to get together now, continue the work that's been done, but start gathering together more this year to lay that out, to actually make sure we are helping to do our job at the Materials Processing Institute and be a catalyst for change in the industry, and use our resources to meet the needs. So we do not work in a vacuum. I'll leave vacuum jokes to the steelmakers, but we need the engagement and the research and development partners. We need the industrial partnerships going forward to actually get these questions addressed properly, in the right level of priority and with the right scale of resources, really, at pilot level as well as at laboratory level, to start addressing these questions. Keep putting your questions in the chats. We will come back to them, because there's so much that we want to learn about using hydrogen and specifically using it in steel. But I'm going to hand over now to Dr. Richard Burley, who will start talking some reality about hydrogen as well. So Richard, over to you.
Good morning. Thank you for the introduction. I'm just going to share my screen. Hopefully you'll get the actual screen view rather than the presenter's view. If somebody could just confirm you've got eyes on.
Yeah, we can see that, Richard, clearly.
Okay, great. Thank you for the introduction and the previous presentations. I get the Grim Reaper's job of highlighting some of the challenges of the production of hydrogen for the steel industry. So some of the topics that we will be covering is reaching net zero, hydrogen in steel, UK energy flow, energy requirement for steel, green hydrogen production, a brief case study, cost of production of green hydrogen, how much hydrogen is actually required, and green hydrogen energy capacity and performance. So if we look at steel making and hydrogen, as Oliver has alluded to, we're using producing steel produces an awful lot of CO2. And in fact, depending on which report you go to, it's between 8 and 9% of the world's CO2 actually comes from steel production. So there's a real need for us to cut the CO2. And if we look at the amount of steel produced, there's 1.35 billion tons of steel, 0.45 billion tons from recycled steel, which is a total of 1.8 billion tons of actual steel produced. So replacing coal by hydrogen generated with renewable energy would make it possible to largely decarbonise the industry, although it's unlikely we would ever be able to completely decarbonise it because carbon is used as part of the chemical process for steel making. So decarbonisation of the steel production processes poses three major challenges: optimising and scaling up hydrogen-based routes of iron and steel production, scaling up the production of hydrogen and therefore producing greater quantities at lower cost with higher efficiency, and evaluating the effects of hydrogen on the output of the industrial processes. So if we look at the steel production and CO2, we can see at 2015, we were producing roughly 2.8 billion tons of CO2. And if we are to reach our net zero targets by 2050, on equivalent values, this needs to be 400 to 600 million tons of CO2. Now, if we project that forward, we know that we're going to be using more steel in the future than we use now. So therefore, the increase in million tons of steel goes from 1.6 up to 2.5. And so therefore, in real terms, we need to see a 90% reduction of CO2 to actually, compared to 2015, to actually try and achieve the CO2 targets. Therefore, we need to utilise low carbon technologies, and one of these will be the increased use of hydrogen as a fuel and a reductant. Reduce energy requirements in the industry, increase energy efficiency, reduce costs of H2 production, and where carbon is required, the potential use of alternate sources of carbon, such as biomass, which can be net zero. So if we look at the energy flows within the UK, this is quite a complex chart, but if I break it down into simple terms, we're really looking at the island steel. We can see that we use natural gas, coal, electricity, bioenergy, and petroleum products. However, apologies. Okay, we can see that the iron and steel uses approximately the equivalent of 0.9 million tons of oil equivalent. This was on 2019 figures, which is only 0.6% of the energy use across the whole country. However, we are producing 8% of the CO2 in the country. Again, this is equivalent to world standards. So we can see that we need to address this problem in the UK as well as globally. So the amount of energy actually used across some of the steel making processes, we look at electric arc furnaces, and at our optimum practical level, we could use 1.6 gigajoules per ton of steel, and in the basic oxygen furnace, 8.2 gigajoules per ton of steel. And so the energy requirements for the production of iron steel with current levels of technology, we could use hydrogen as a fuel and as a reductant. And as shown in the presentation previous by Oliver, there are various areas within the steel industry that hydrogen could be slotted in. So steel making and hydrogen, and if we look at electrolysis for green steel global DRI production, 1 ton of finished green steel will require approximately 3.5 megawatt hours of hydrogen, which equates to approximately 90 kilograms of hydrogen per ton of steel. So the electrical energy required to produce the hydrogen and for the ton of steel would be between 4 and 4.5 megawatt hours, depending upon the exact DRI that you're using. So the electricity required to create the hydrogen to make all the world's green steel at today's production levels would be 459 terawatt hours of hydrogen, on the grounds that DRI produces 108 million tons of steel. If the average new wind turbine has a capacity of 40%, realistically 30, sometimes as low as 17, then the world would need 84 gigawatts of extra wind turbines. Now, if we put this in perspective, Hornsea 1 is the largest offshore wind farm in the world, producing 1.2 gigawatts and has a surface area of 407 kilometers squared. And they're using 7 megawatt turbines, and there are 174 of those in total. There is an increased planned capacity up to 6 gigawatts. So if we put this into perspective then for hydrogen DRI, if we were to only use wind turbines at 7 megawatts, then we would need nearly an extra 12,000 new wind turbines just to provide the energy required for DRI. So if we put this in perspective on the world wind power generation, the average size of wind generators is 2 to 3 megawatts, and the world wind electricity capacity is 751 gigawatts. Now, the 84 gigawatts might seem an awful lot to achieve. However, if we look at wind energy added in 2019, there were 60.4 gigawatts. So 84 is not a massive leap in imagination. It's just over 1 year of extra wind capacity, wind electrical generation. However, to put this in perspective now for all global steel, DRI is only about 8% of the world's steel production. And therefore total world steel would need to produce 5,700 terawatt hours of electricity for the production of hydrogen DRI. So in perspective, we can say that's 12 times the amount, so that would be approximately 144,000 7 megawatt wind turbines. And this is 1/4 of the world's electricity production as of 2019. So wind turbines alone are unlikely to be the solution. However, a combination of solutions for the extra electrical power and a combination of hydrogen to production methods is likely to be what's required. So steel making hydrogen, cost of hydrogen production electrolysis in the UK. Now, 100% efficient electrolyzer uses 39 kilowatt hours per kilogram of hydrogen. Again, realistically, we're never going to get 100% efficiency. So we can say that that's equates to 48 kilowatt hours per kilogram of hydrogen. Now, in 2019, 36.9% of UK electricity came from renewable sources, with a maximum renewable capacity of 170 terawatt hours. Now, the UK plans to increase its wind capacity to 40 gigawatt hours. That equates to roughly 350 terawatt hours. And the average cost for standard electricity in the UK in 2020 was 17.2 pence per kilowatt hour. If we look at the industrial rates at 12 pence per kilowatt hour, when we compare this to the gas average cost of 3.8 pence, we can see that the cost of electricity is far more expensive than running our steel industry on gas. However, some energy providers on cheap rate electricity do go as low as 4.5 pence per kilowatt hour. So if we put this in real terms for hydrogen production, we can see that at 4.5 pence, it would cost £2.16 electricity in an electrolysis process per kilogram of hydrogen, and £5.76 at the industrial rates. Now, a blast furnace consumes about 3.68 megawatt hours per tonne of liquid steel, mainly coal and coke at the moment, and hydrogen steel-based steel making consumes approximately 3.48 megawatt hours per tonne of liquid steel, mainly electricity. So the hydrogen required in the UK would be approximately 28 to 29 terawatt hours of hydrogen, and the UK currently produces only 27 terawatt hours of hydrogen. So we're going to need to increase our hydrogen production in the UK. So hydrogen from electrolysis, then UK integrated plants such as Port Talbot and Scunthorpe would increase on-site electricity use by 16 times. And the steel sector overall would increase electricity consumption from 2.5 terawatt hours to 21 terawatt hours. This is an 8.5 times increase, which is the equivalent to 6.5 million UK household electricity demands. These figures are similar to those quoted from Hybrid in Sweden, which says 6 to 7 times the increase. So UK estimates for hydrogen production using steam reforming is approximately £50 per megawatt hour, and that's 2 times the cost of using natural gas. And projected, so the cost of hydrogen is projected to decrease to 40 megawatts hour in 2030, and hopefully down to as low as £20 per megawatt hour in 2050. To put this in perspective then for crude steel production, if we were to use electrolysis, the energy costs alone for electrolysis would be between 160 and 426 pounds per tonne of crude steel, and the current energy costs come in at 120 pounds per tonne of crude steel. So briefly looking then at our renewable energy capacity, of 100% of our energy capacity, 35% of the renewable source is in the form of electricity. So the electricity may well provide a source of renewable energy for producing the hydrogen. Now, I've taken a snapshot here, 17th of May. As we all know, 17th of May was when we started opening up restrictions, thanks to COVID. And we can see from this that only approximately 21% of renewable energy was used for our electricity production. And interestingly, we got 7.4% interconnectors. An article I was reading this morning says that one of the problems with UK electricity is transmission costs, which is one of the highest in Europe. So therefore, it is often cheaper to import electricity than it actually is to use our own, which is a sad state of affair. So if we project this forward then and we compare grey hydrogen to green hydrogen, if we carry on as status as normal, electricity needs to be as low as £10 per megawatt hour for electrolysis to be cost effective against natural gas. If the UK were to be competitive green hydrogen, DRI would need to have a price of renewable energy below £25 per megawatt hour, with a carbon taxation price of £50 per tonne. The EU is heading towards a carbon taxation of €50 per tonne of CO2 equivalent. And the UK, after leaving the EU, had an auction price of £18 per tonne of CO2 equivalent. So we seriously need to consider the carbon taxation to actually make green hydrogen cost effective by 2030 or 2040. So a summary of what we just looked at then, the steel industry will need to make significant changes to meet future carbon emissions targets. The use of hydrogen as a replacement for fuel and a reductant can be an important part of the carbon reduction strategy. UK steel production uses a small amount of energy in relation to its emissions, particularly CO2. Wind energy could form part of the energy mix to produce hydrogen from electrolysis. However, large builds will be required to produce the amount of H2 required purely from wind. UK does not use green energy to its full capacity or its capability. And for hydrogen from green energy to be cost effective, cost of production needs to fall and cost of tax, carbon tax, needs to increase. Future webinars, the dates are to be confirmed. However, we are scheduled for a second and a third webinar within this. Some of the areas that will be covered within this are direct reduction of iron processes to feed electrical steel making, hydrogen as a reductant in DRI, hydrogen as an auxiliary reductant fuel in blast furnaces, hydrogen for heat generation, opportunities and challenges for the steel process, hydrogen for electrical power generation and storage, and challenges of handling and storing hydrogen and its effects on steels. Thank you very much for listening, and I believe the forum will be open for questions.
Great. I'll thank Richard first on behalf of Materials Processing Institute. Simon and I agreed that we would try and triage the questions that have come through. So Simon, I'll defer to you to start with, if there's anything you'd like us to pick up on.
No, actually, most of these seem to be focused around steel manufacturers. So I know some of your team have been answering some of the questions in the background. So we'll send to a few steps.
We do our best to answer them as they come along. If we start with some of the, I suppose, headline comments, which Richard was trying to put some reality into as well, about the scale of how do we move from people waving their arms and saying everything will be electric and hydrogen and we'll just do it, to the reality of where the industry is at right now, and the steps we need to take. Rather than me commenting, would one of our team like to put a bit more comment on, particularly Andrew Purvis summarised it well about the message. Is the message hydrogen is not the only solution? The bigger picture. Somebody care to comment live on that for us? Colin, are you online?
Yeah, just waiting for my microphone to unmute. It's things to be a bit sluggish this morning. Yeah, I think in your response to Andrew in the chat, I think you're quite right that hydrogen is not the only answer. We can't just rely on there is no, as you say, there is no silver bullet. There is no one single solution. In terms of the chemical processes that we've got to consider in making steel and also in making other metals from primary ores, is that there's got to be some process for getting that metal out, reducing that metal. And at the moment, in the iron making process, the major reductant is carbon, whether that's in the form of solid carbon. So there's a solid carbon liquid metal interaction, or whether it's secondary reduction by mainly carbon monoxide and by some hydrogen in the blast furnace. We've got to find a replacement for that carbon. Now, we talked about the length, the lifetime of current assets, blast furnace assets around the world, spanning a timescale of about 40 years. That would mean that you need to be thinking now about replacing those primary units, because the blast furnace is not going to be part of the long-term solution. The blast furnace is still going to have to be phased out of the process if we're going to get CO2 emissions down to the levels that are required by the commitments that the UK government and other world governments have made in order to keep global warming down to less than 1.5 degrees centigrade change, and to prevent major effects on the general climate. But yes, hydrogen's part of the picture. If somebody can come up with another fantastic process that's going to be as energy efficient and cost effective, for example, there's an outfit in the States are investigating, and I believe Bill Gates has put money in as well to this outfit, looking at direct electrolysis in a process that you could say is similar to aluminium refining. That may be an alternative route. So that's using electricity, but that means the electricity demand is still going to be a lot higher than it is today, in order to ensure that there is enough for industry to be able to commit to using those processes. So it's a very complicated picture. It's a very complicated landscape. Hydrogen is part of that. This series of webinars is about hydrogen, what hydrogen can do, how we can possibly use it. But it does seem a bit bonkers when you think about it, that you're using energy, electricity to make hydrogen, and then you're going to burn it to get the energy back. Why don't you just use the electricity in the first place? And Andrew's made a good point. In areas of reheating, especially steel stock, which you can heat by resistance heating, for example, or inductive heating, perhaps, then that might be the route to follow. But that still requires a lot of energy. That still requires a lot of electricity, and the demand for electricity is going to rise.
Thank you. While we're looking at electricity and energy flows around steelmaking, there was also a question basically referencing the fact that the steel industry is incredibly good at reusing gas and waste heats and all sorts of different gases in process. Colin or Tony, if you're online, would you care to comment on the potential that introducing hydrogen in there would have for disrupting existing kind of efficiencies in terms of reuse of process gases? And also, obviously, we're not doing this is not a seminar on capturing carbon capture, but that's the other end of, if you're using hydrocarbons, what do you do with the carbon bit of it? Any 2 or 3 minutes on comment on that, and then we'll perhaps move on to some other issues about burning of hydrogen.
Yeah, I mean, if you like, that is the elephant in the room. In an integrated steelworks, one of the reasons why an integrated steelworks is so efficient is because it reuses all these works arising gases. So the coke ovens produce a lot of high calorific value gas, which is funnily enough largely hydrogen, and then that's mixed with the blast furnace gas or the boss gas, in order to give you a works arising gas that's got a consistent Wobbe index and calorific value for use around the patch. And then that's used as a fuel for the reheating furnaces. It goes back to the coke ovens. It goes to the blast furnace for the blast furnace stoves. And if you're going to be introducing hydrogen and displacing those gases, well, what are you going to do with those gases? And this is one of the fundamental issues of trying to square the circle of introducing hydrogen into an existing process. The main route for use of hydrogen will be into alternative iron making processes. So the HDRI route to the electric arc furnace, that does away with the coke ovens, the blast furnace, the sinter plant, that all produce huge amounts of CO2. But then because you've now got a gap in your works arising gases, if you take those out, then that's when hydrogen has to be considered for reheating and heating purposes, for rolling, finishing of the steel materials. So looking at a current integrated steelworks, blast furnace Boss route steelworks, then it doesn't make a lot of sense. But you're going to have to start doing something to bring those CO2 emissions down. And I agree that CCUS is the route for doing that. But you will see that there will be quite a clamour from environmental organisations saying that CCUS isn't the ultimate solution. There's still the problem that you've got of using the carbon dioxide that's being captured, storing that carbon dioxide long term, and the danger, or the perceived danger, that CO2 is going to leak back into the environment.
Thank
I don't know if you want to add anything to that, Tony.
I was just thinking back to Chris Vaughan's comment then, can hydrogen be used in the blast furnace? And yes, it can be. And then there is thermodynamic limitations, and those calculations will have to be considered then in research and going through. But there is the issue then, obviously, if can the blast furnaces be phased out completely? At this moment in time, that is extremely difficult then, because we don't have all the answers, and electric arc furnace steelmaking isn't not all grades can be produced by electric arc steelmaking at this moment in time. So work on that side also needs to be required, required as well. Then and yes, we do have ThyssenKrupp injecting hydrogen into a blast furnace. Then someone has just commented as an ongoing trial at this moment in time. Then but obviously there hasn't been too much reported on that, as far as I can see. So yeah, there's still plenty of challenges ahead then for this, without a doubt.
Thank you, and I'll just make a brief comment, because I mean there's some great comments popping up from actual practitioners in the chat, which is what we need. There is some work to be done together, making sure we have the best, most accurate, most relevant models from the thermodynamic side of things, but also from the whole process modeling things, and then apply best practice in life cycle analysis and well, basically carbon emission modeling, so that we can intelligently and practically work together to actually say, yes, we can use hydrogen or electricity or other low carbon or zero carbon technologies to produce steel, but look at the effect on the entire system and the people involved in making that as well. There's an awful lot to catch up on, and we do have plans for following up these seminars with more specific looks at particular bits of the technology, particularly the more disruptive side of using hydrogen as direct reductant for metal ores, iron ore in particular, later on. We will be collecting comments here and hopefully using this as a bit of a catalyst, a forum to get kind of wider conversation and chat going on these issues. There's work being done across the world on in many of these spheres as well. So we don't need to be reinventing the wheel, but we do need to know what the wheel is doing and where do we come in to make the most of that. I see Simon has popped up as well. I think given that our time is coming to an end, and we do want to look in more detail at reduction, but also some of the other associated issues of the increased use of hydrogen, whether that's the actual impact of hydrogen on steels. And one question we want to be answering, what if you're burning pure hydrogen in a reheat furnace, what's that actually going to do to some of the stock and the surrounding materials? But also this issue of NOx in hydrogen combustion is a major one too. That's a subject for another time, I think. Simon's nodding.
Yeah,
I'll hand back to Simon and thank you.
Yeah, no, I want to thank everybody for joining us this morning. I hope everybody's found this really interesting, really helpful and informative. as Mark has said, we're looking to do a series of webinars later in the year, and we'd love you to come and join those and participate. You've obviously heard, you've got some contact details for the Materials Process Institute. They would love to hear from you today if there's anything that you want to collaborate with them, as well as Teesside University. At this point, I think we'll just call it for a close day. I think we could be running for another half an hour or more with questions and comments and things, which is great. It shows a lot of interest in this area of decarbonisation. And I look forward to meeting everybody again very soon. So thank you very much for your time today, and thank you to everybody who's presented today.